and refresh. So what we were dealing with in section 12.3, the section that may seem to be very lengthy and tedious, but on the other hand, I will try to make it be nice and pleasant. The section that is dealing with so-called standard deviation. So what does that actually mean? Well, it turns out that every sample that you can ever select, given in terms of numbers, has two characteristics: sample mean and the sample standard deviation. Sample mean is sample average. I'm trying to just look at the example that they have here to give a bit of intuition into what is going on. So they have a sample somewhere. Let me get there. And so, for example, here's the formula that I was trying to come up with last time to actually justify it. That's a special formula for so-called standard deviation. Also, we utilized this formula and went through example that they have here. It looks like they have only one example considered. It's right there, example 4. So we looked at that example 4. So what we have noticed and found that in example 4, in a sample A, in the first part, we had mean for the sample equal to, right there, 20, right? And then we also noticed they found the standard deviation, and we did it also with a calculator. The standard deviation, called as letter S, equal to 2.16. So let me write this because I know it's kind of hard to keep this all in mind. So that's a mean. In other words, the average. Of course, it's for sample, so that's why it's a sample mean. And also so-called standard deviation, right? Standard deviation. So those two special numbers were really special because if you have the sample mean of 20 placed on number line and move to the left and to the right by that sample standard deviation, then you should have a description of a ballpark for all the sample elements. So you will see that this be adding 20 with 2.16 is like 2216. So if you add it with 20, or if you subtract, so when you go to the left side, you will subtract. You're going to get 17.84, something like that. So that tells you that your sample is somewhere close to those boundaries. It's not within those boundaries, because indeed, if you looked at the sample elements that are right here, 17 all the way through 23, then these sample elements are stacking a little bit out, like 17, then there is a 18, 19, 20, 21, 22, and there is 23. So a couple of sample elements are on the outside of this boundaries, but it gives you an idea of where they all are. So the point is, all elements don't have to be inside of these borders that I just put with this A1784 and 2216, but they're close to them. And that's the idea of standard deviation. It shows you how far sample elements are spread from the center, from the sample mean. So to calculate standard deviation, we last time used the online calculator, and I'd like to use it again for some exercises here. I think I did number 10. So let me try one more that asks about mean and standard deviation. So let's take something not as nice looking like exercise number 15. So to be able to do problem number 15, let me look at the sample elements here. So they range from 1.9, looks like that's the smallest. Then there is a 225, 275. 75. You don't have to rearrange them. I'm just trying to show you that what we are going to calculate would make a little sense. 3.1 and 3.5. It looks like we have here sample that consists of 5 elements. And I want to find its mean and standard deviation. So the way we did it, I went to this search engine and typed standard deviation calculator to get a free calculator to get my standard deviation. So once I searched for it, the first choice is what I used, the standard deviation calculator. So if you have an issue, difficulty to do the search, I can put the link so you can click on it and get to this calculator right away. So I just put this in the Zoom chat so you can look at the chat and just click on that link and calculator should open for you in the other window. So next step will be to carefully enter this data in that calculator. So I want to enter all of the numbers here. So let me put them so I can see them. And I need to use commas. So that's the tedious part. So you need to put 1.9, put a comma, space. Next is 225, and so forth. It's 275, 3.1, 0.1, and also 3.5. Right? So we have entered these 5 sample elements. Now, important part, treat it as not a population, but a sample, right? Because we're looking for the sample standard deviation. We're never going to look for population standard deviation in this class. And here's, after I clicked calculate, right away the calculator gave me sample mean, the average, and this is right here, 2.7, right? And the standard deviation for this sample, which is 0.641 dot dot dot. So I can just put 641, something like that is good enough. 3 digits, I think, is plenty in here. So we have answered their question. So the question was find the mean, the standard deviation from mean. And that's all I want. Well, sum of standard deviations, I don't think you want to do that. So you find mean and standard deviations. And the whole point of this is to show that your sample has a mean 275. Please notice it's somewhere a little less than, oh, sorry, 2.7, 2.7, a little less than element 275. And then standard deviation of 0.641 tells you that you should go by 0.6 to like up to element 2, right? So standard deviation 641. So if you subtract 0.6 from 0.7, you'll get like 2 and a little something. So a little bit more than 1.9. And if you add 6 and 4, you get a 13. So 13 will be like somewhere, right? So it looks like usually we have the elements on the right and the left that stick out a little bit from your borders for standard deviations. But we can see that this is a pretty good intuitive description for the sample. So all we do, we just put numbers in a calculator, and a standard deviation calculator that I just put here in the Zoom chat for you, using commas, and get the answers. So that's all you need. And that's great, I think. So this section is pretty short, just one standard deviation, although it takes a while to compute it if you do this by hand. So I'd like to move on to the next section, see what else we have here in chapter 12. So it looks like next section of chapter 12 is talking about so-called normal distribution. And it turns out that word normal is here because on the planet of Earth, everything is distributed normally. And what normal actually stands for is this particular shape that they show here in the part D. So, for example, if you look at people's heights, you will see that the heights distributed normally. And the other thing to realize that mean, the average, will be always in the center. So this is our x-axis, and this is our, turns out, probability axis. So for every x, let's say height is 6 feet, there is some probability that this height will appear that's on the y or function p probability of height will give us the result. So that's interesting to realize, normal distribution. And of course, if you look at the sample, because when we're talking about normal distribution, it means how entire population is distributed, all people on the planet of Earth. I say, well, it's gonna take Alex a while to measure the heights of all people on the planet of Earth, because some people may come to the planet, some people may leave the planet, so like being born or die, so we might have to constantly do it because it just keeps on changing all the time, right? The population. And that's the reason why we don't even want to think of entire population. We take part of it called sample. And we can say for sample for every element. So let's say for this person, I can measure the height, and height will be here. For this person, I measure the height, height will be here. So if I take a sample here with 1, 2, 3, 4, 5, 6, 7 heights, or if I take more, or notice if I take even more, and the more heights I take, the closer picture will resemble that so-called bell-shaped normal distribution, the one that I have in part D. So when you are dealing with entire population, the part D appears, but if you take just portion of population, you have different little segments of it. So I can talk about this normal distribution, and the main observation is to notice that it has its center at the mean. And then what they do is they look at the special distribution, so-called standard normal. So the standard normal distribution has its mean at 0.0. Because your mean could be anything, the average for people's height, maybe like 5.6, 8, whatever. And for sample will be different. So it's definitely not a 0, right? But it turns out there is a distribution called standard normal that has a 0 as its mean. And again, mean is always here in the center. So good observation is that the picture is symmetric. So if you have a mirror along the, I would say, x-axis, because that's a 0 here, then the left side reflects to the right and vice versa. So that's interesting thing to realize about the so-called normal distributions. So we also have a bit of a story associated with it in this little section. So they talking about this normal distribution, and then they also, of course, mention how we can possibly convert any distribution to the so-called normal distribution. And what they do, because idea is that we really pretty much never have distribution with mean zero. It's very rare, right? But our population mean could be any number. Like here they have 7, for example. It's like newborn infants. So they say the average weight is 7 pounds. Okay. So the idea is that they always trying to convert this distribution to normal, to that standard norm with a mean equal to 0. I say, Alex, why would they do this? And the answer is they have a special way to find various values for this. And we'll be talking about those special ways next time. But for today, they trying to always use a little formula that says x minus mean over standard deviation. So please notice that mean for population is not the same as a mean for the sample, because it's population, it's everything. So we call it as mu, that's a mean. And for the standard deviation, we'll also use a special letter called sigma. It's a standard deviation, but for the population. So in this section, they are talking about converting any population to that distribution with mean equal to 0. And they give you the formula. And right now, I want to practice just using this little formula just to start to get used to this idea. So I want to look at the exercises that appear here that talk about that little conversion. So let me go to the section end and try to convert some of this z-score, like, for example, exercise number 33. So I think for homework could be a good idea, just look at this group of exercises for now. Don't worry about the others. We'll talk about them next time. So if I'm looking at exercise number 33, that talks about mean of 60, our population has mean of 60, with a standard deviation equal to 8. So that's a standard deviation, sigma equal to 8. But you say, Alex, is that 6 or that's a sigma? No, that's a sigma. That's a special Greek letter sigma, just like a letter mu. In Greece, they don't have letter M. They like to use mu. Instead of letter N, they use nu. How about that? Instead of letter A, they use alpha. So they like to put this little tail for some reason to those letters. So sigma, that's something like that. And that's what we're using for standard deviation. So it's not really a 6, that's the point. Oh, okay. So they say if you want to convert x equal to 68 to that special so-called z-score that we'll be talking more about a little later, z-score, then it turns out that I'm gonna have to use the formula x minus mean over standard deviation and try to convert it. So how do I do this? Well, we have 3 numbers that patiently waiting for me to put them in the formula. Instead of x, I have 68, it's right here. Subtract instead of mean, I have number 60, right? And instead of standard deviation, I get 8. So please notice that z is going to be equal to 1. I divide 8 by 8. And say, Alex, are you sure? Well, I can put it in your calculator. Let me do this. So you can go with a parentheses. Then 68 minus 8 in numerator. 68 minus 60, sorry. 60, right? I put parentheses to make sure it's entirely divided by number 8. And you see what I got? Number 1. Just like that. So it is not too bad, right? So let me do one more like that. So please notice that we no longer deal with a sample. Now we move to the story of population, everything. And turns out we have to somehow be able to tell them apart, sample or which is a part of entire thing, which is a population. So let me try another one, like number 36, exercise 36 that says, what if you're dealing with a x equal to 92? Find a z-square, that z, which is x minus mean over standard deviation. Well, it looks like I'm going to do pretty much the same thing. I'm going to use 92 instead of x, right? Subtract mean, which is 60, and divide this by 8. So I'm going to divide 32 by 8. So probably it's going to be something like that. Let's double check with a calculator. So let me put this in the calculator once again. So I put this parentheses, 92 minus 60 parentheses, and divide that by 8 and get 4. But that feels good. So it looks like we just starting to get used to this. I know one may have tons of questions asking why we do this or everything. Well, so far we're preparing for a further interesting stories. And that's why maybe it's a good idea that you also prepare, try exercise number 34 as a little quiz. So just repeat the exact same thing I did in exercises 36 or in exercise 33. So use this conversion formula and tell me what do you think z will be for number 76. So it looks like all you have to do is replace, like I did in these exercises, with 76 those values of x, right? So just do this carefully, and this be today's quiz. So just let me know the answer, and after that you can enjoy your weekend.